Hello everyone, let me present today research entitled Morphology and Properties of Boron-based multi-component coatings and diffusion layers on the surface of tool steels. Boron-based coatings and layers are capable to provide high physical and mechanical properties, and they can be synthesized on the surface of machine elements and parts by different surface engineering techniques such as thermal-chemical treatment and electron beam surface modification. I'm going to start with motivation to do this particular research, then surface engineering techniques, including Boriding and its features. Of course, materials, objectives, and methodology will be also shown. Then, research result will be presented by thermal-chemical treatment, then followed by electron beam surface modification, and in the end, residual stress measurements and surface roughness reduction will be shown. On the upper left, you can see Mi-171 helicopter, which is deep modernized version of well-known Mi-8 helicopter, and rotor blade erosion shields made of titanium alloy with a specific profile, and this profile can be achieved by using following procedure. So billet before punching. Heat it up to a temperature of around 800 degrees Celsius. Then, when desirable profile can be obtained between die and punch. So this U-bending die is made of steel H21. Is actually our our motivation of research. Surface engineering techniques can be roughly divided in two groups: diffusion-less processes and diffusion processes. And among the second group, thermal-chemical treatment is in high interest because of ability to provide enhanced mechanical and physical properties with favorable costs. Thermal-chemical treatment can be made at high temperatures in chemically active media, where element A diffuses into surface of metals and alloys and form compound layer firstly, then solid solution or transition zone, and the concentration profile in most cases have a smooth slope like here. And among TCT methods, Boriding is capable to provide many attractive properties, such as high hardness, low friction coefficient, high wear, erosion, corrosion, and oxidation resistance. So as a result of treatment, a tooth-like microstructure consisting of ferrum boron as an outer phase and ferrum 2 boron as an inner phase layer can be obtained. And despite the number of advantages, Boriding has limited application because of high brittleness of ferrum boron phase and tendency to spalling and crack formation. This is due to thermal expansion anisotropy of iron borides. Besides, it is known that ferrum 2 boron produces compressive residual stresses while ferrum-boron tensile ones. So there are several methods of brittleness reducing of borate layer. The first group of methods is designed to obtain a single ferrum-2 boron layer. And the second way is multi-component treatment. This way can be also divided into sub-methods. First, where both alloying diffusion elements are non-metals. These methods are borocarburizing and boron-nitride, and the second group of methods where the second element is actually metal. These methods are borochromizing, boronickelizing, borotitanizing, and boroaluminizing. The latter method is a combination of boriding and aluminizing, where iron borides provide high mechanical properties such as wear resistance and high micro hardness, while the iron aluminides provide high oxidation at high temperatures and plasticity for the entire layer. So the third method of brittleness reducing is combined treatment, where ferromechanical treatment can be done as a first step and followed by high-energy fluxes treatment. As an example, boriding can be done as a first step, and the second step can be done by electron beam processing of specific places on dies. For instance, this top part and the corner, they are subjected to severe wear because of high metal flow rate, and they need to be additionally modified. So now hot work tool steel, free hot 2V8F was used as a tested material. It is analog to STM H21 steel. It contains high amount chromium, tungsten, and vanadium, which guaranteed the high mechanical properties of this steel. And for convenience, STM standard grade will be used for this presentation further. Based on what have been said, objectives of this research is to improve physical and mechanical properties of hot work tool steel by means of different techniques such as TCT, electron beam alloying, and combined treatment, and to reduce brittleness and surface roughness of boride layers by adding aluminum powder to boriding agent. So after different surface engineering techniques, samples were subjected to common sample preparation procedures and structure, composition, and different tests, and were conducted, including residual stress measurements and surface roughness reduction. Before treatment, samples were cut into rectangular pieces with these specific dimensions. Then, as boron and aluminum sources, boron carbide and aluminum powders were used respectively, and a small amount of sodium fluoride was used as an activator. And for boroaluminizing, aluminum and boron carbide ratio was taken as 1/5. Treatment powder was mixed with organic glue and ethanol until achieving pasty condition. Then sample and treatment paste were placed in cylindrical molds. After a while, molds were removed and obtained briquettes were dried. And dried briquettes were placed and preheated to treatment temperature furnace for 2 hours. And after exposure, samples were removed from furnace and cooled down to ambient temperature. So after that, so samples can be easily separated from dried paste. So as a result of treatment, so different microstructures were obtained. So after boriding, two-phase layer was obtained with tooth-like microstructure and with a thickness of just above 100 micrometers. After boroaluminizing, complex microstructure was obtained. With a thickness of around 560 micrometers. So several specific zones can be distinguished in this microstructure. So zone 1 contains ferrum boron needles and precipitation of carbides on top and iron aluminide. Zone 2 contain elongated and small crystals of carboboride and displays placed and matrix of solid solution of aluminum in iron. So magnified picture of zone 3 revealed bainite surrounded by a net of carbide. And we also provide FM analysis to obtain 3D picture and to measure elastic models of obtained layers. And this analysis showed that maximum boron concentration after boriding is on top of the layer and correspond to ferrum boron phase. And it is also should be noted that boride layer is highly alloyed with tungsten, chromium, and vanadium. After boroaluminizing, the maximum boron and aluminum concentration is also on top of the layer in zone 1. And in zone 2, there is a high amount of tungsten, up to 56% in zone of carboborides. And we can see also how aluminum diffuses. The maximum it diffuses up to zone 3, and its maximum concentration there is 5.11%. So boriding provided high micro hardness up to 2900 HV. This actually quite high because, and probably due to alloying boride layer with tungsten, chromium, and vanadium. Then in transition zone, micro hardness values drastically dropped to around 600 HV and remained fairly flat. So microstructure diversity and phase diversity of boroaluminized layer resulted in micro hardness value variation. You see blue line where the maximum micro hardness is in zone 1 and the minimum in zone 2, and the second peak is visible in zone 4, which correspond to carbide rich zone. XRD analysis showed that boron nitride and aluminum nitride form after treatment, which is probably due to interaction with air components. The same can be also corresponded to oxide formation, chromium oxide and iron oxide after boroaluminizing. So now one of the crucial properties of borided layer is wear resistance. This test was done according to block on ring scheme, and the contour part was hardened steel of high-speed steel, And it is obvious that clearly visible that boriding, both boriding and boroluminizing resulted in enhancement of wear resistance of H21 steel. However, wear mechanism differs. So after boroluminizing, it is necessary to say that galling is the principal mechanism of wear, and after boriding, low welding tendency resulted in high wear resistance. EDS analysis showed that the presence of high amount of oxygen in both cases, which is probably a signal of triboxide presence and formation during wear test. So the next treatment is electron beam surface modification. We came to this step, and this method of surface engineering can be also divided in two ways: electron beam alloying and combined treatment, where the first step is TCT, one of TCT methods, boriding or boroluminizing, and the second step is electron beam processing. So surface modification was conducted on vacuum pulse electron beam energy complex solo, and the second installation is electrovacuum power machine. So the results in present research will be from results obtained on this second installation. Electron beam alloying resulted in coating formation with a thickness of around 300 and 500 micrometers. After a single boron carbide alloy, we see a lot of dendrites placed in light matrix, and magnified picture showed its cellular structure. After two-component alloying, we see that rhombic crystals form. These are probably iron borides, and they contribute to enhanced micro-hardness, as we can see here. So micro-hardness after two-component alloying is much higher than single-component electron beam alloying. Electron beam processing resulted in significant microstructure transformation compared to the first step. TCT here is boroluminizing, and we see that after electron beam treatment, so we obtained highly homogeneous coating with a thickness of around 1 millimeter. And phase analysis showed that there is also high transformation here took place. So firstly was revealed tungsten boride. For the first time was revealed. And magnified picture, SAM picture, showed that solid phases such as iron borides and carbides after electron beam processing became much smaller. And this contribute to micro-hardness distribution. As you can see, the red line is values after combined treatment, and this pattern is much more even compared to micro-hardness profile after first step boroluminizing. Here, let me point your attention to aluminum distribution. After first step, boroluminizing, aluminum mostly concentrate in the top of the layer, and after electron beam processing, aluminum concentration became more even. Control residual stresses is a very crucial issue of mechanical engineering and surface engineering as well. So we conducted this test and experiments in our partner institution in Irkutsk National State University, Technical University, and this test were conducted on UDON2 installation, which is presented here. And on the bottom right, we see test samples before and after conducting tests. And here you see the zone after etched zone is clearly visible. So experiment procedure contain run experiment, chemical etching, recording deformation curves, weighing, and average etching rate was conducted according, was calculated according to this equation, and then residual stress calculation was done in XUDN software. After that, construction of diagrams was done and for formation of protocol on measurements. As you can see here, Boriding resulted in mostly compressive residual stress distribution in upper two graph, and bottom two graph boron-aluminizing resulted in mainly in tensile residual stress distribution, which is less favorable for our application. If we put in correlation micro hardness distribution, we see that these graphs correlate well, and high gradient of values is visible on both graphs after residuals, stress measurements, and micro hardness for low temperature boriding. As for high temperature boriding, there is no such high gradient values. There is a smooth slope in both cases after residual stress measurements and after micro hardness measurements. So which is quite good and favorable and desirable for application from application perspectives. So to ensure surface quality, it is necessary, and life expectancy, it is necessary to minimize surface roughness of tools and machine elements. So this can be done by boron nitride, cubic boron nitride cutting tool, and as a grinding tool, and so surface roughness was measured on optical profilometer. So it is visible that from mechanical treatment resulted in higher surface roughness. As for boriding, we see initial 1.5 micrometers increased to 4 micrometers initial error, and to 7.7 micrometers after boron-aluminizing. And subsequent CBN grinding resulted in surface roughness reduction to 0.09 micrometers and 0.43 micrometers after boron-aluminizing. So, we came to the end of report, and whereas so based on conducted research, there were several conclusions. So firstly, it was shown that boriding resulted in formation of an ferrum boron, ferrum two boron layer with a tooth-like structure. A completely different microstructure was revealed after boron-aluminizing, namely diffusion layer with heterogeneous structure. The layer thickness increased from 105 micrometers to 560 micrometers compared to pure boriding. The maximum micro hardness values reached 2900 HV after pure boriding, while for boron-aluminizing it was around 2000 HV. It was revealed that the mass loss during weird test reduced by 2 times after boron-aluminizing and 13 times after boriding compared to hardened sample after 5-minute testing. So electron beam alloying leads to coating formation with a thickness up to 500 micrometers. Micro-hardness of ferrum or boron carbide aluminium electron beam alloy is much higher compared to single boron carbide alloy. The combined processing method results in equalization of phase composition of layer thickness and obtaining structure with uniform composition. And it was also found that boriding at 950 degrees led to a more favorable distribution of compression, residual stress, and diffusion layer. An increase in thermochemical treatment temperature led to tensile residual stress appearance in the upper zone of layer up to 50 micrometers from the surface. And the last surface roughness of diffusion layer can be reduced by CBN cutting tool by 44 and 18 times after boriding and boroaluminizing respectively. The provided surface quality ensures sufficient operational properties of the meshing elements and tools. So, and let me also acknowledge the Vebleo platform to deliver research, and also to our supporters, Russian Science Foundation, and our partner institutions and their staff and students from East Siberia State University of Technology Management and Irkutsk National Research Technical University. So thank you for your attention, and if you have questions, I'd be happy to answer.